So he has in here that this is 350. Like I said, I don't know. It's not in the problem statement that he put out, but we will use that. And X1 is 0.38. Conversion doesn't change across the heat exchanger. And so is there anything that we don't know in order to solve for the in order to set up the problem? Are we good now? Okay, how does the other equation that we had change? The Van Hoff equation.
It doesn't, but it's just a different temperature.
Right, nothing else changes, it's just a different temperature. So you take that equation, you take the Van Hoff equation, you solve them simultaneously, and you get and so now what's the conversion coming out of the second reactor?
0.95 times that.
Times that, or times the difference between that and X1? No, it's just times that. I'm just being tricky. Because remember, the problem statement said of equilibrium conversion. So as long as that's the equilibrium conversion, it's not the difference. Actually, this is, sorry, read it wrong. Not that it matters, but I know you guys go home and check all my math, so I want to make sure you got nothing better to do. And then we plug that back into T2, back into this formula, and we get 431 Kelvin. Okay, what about problem 3? You guys want to derive it again? So what changes, right? Nothing, except this is now the temperature entering the third reactor, and this is the third conversion minus the second conversion. You do the same exact solution, same procedure, and what you get is the equilibrium temperature. The third equilibrium temperature is 428. The third equilibrium conversion is 0.78. You use that to get the actual conversion coming out of the reactor to 7.4. And then you use that to get the actual temperature coming out of the third reaction, which is
And is T0 3 equal to 350 also?
that's a good question. He doesn't write it down, so we'll assume that it is. Yeah, it is.
Okay.
Yeah, so that's, again, you're going to have to be told something about these heat exchangers. You might be told the difference, right? You might be saying it's going to cool it by X amount, 10 degrees. You might be told the load, and then you can calculate the heat, the temperature drop by using the heat capacity. You might be told simply the outlet temperature is going to be 350 every time. But you have to be told something about how those heat exchangers are operating. Okay, so we'll put this now on the plot that we're all becoming so fond of. Okay, so this is the inlet temperature going into the reactor. And now, what's my initial conversion? 0,
Yeah.
right? And then what were my intermediate conversions? Can someone read them out? I mean, I can see the third one is 74.
0.4. Oh, wait, no, I'm sorry, with the multiple
Point
reactors,
38.
yeah. It
Yeah.
was 0.38,
Yeah.
and then it was 0.582.
582. Okay, so we come up here and we stop, whatever that point is, and then we come back to what temperature?
350.
And then we come up here, come back, come up here. Any questions about how this works? Yeah.
If we were to do this with delta CP not equal to 0, could
Yes.
we use that less simplified equation with a difference in the convergence?
This
Or-
one up here?
Yes, could we use that with a difference in convergence? So x2 minus x1 for all the
Yes.
x's? Okay.
Yeah, it should still work out.
Okay.
Any other questions? Yeah.
How did you find the XE2? Are they one equal to
The same way that we found the first one. So you have the Van Hoff equation, which is, well, you have this equation, which is going to be the equilibrium constant at what temperature? The second equilibrium temperature, divided by 1 plus the equilibrium constant at the second equilibrium temperature. And then you have that this is equal to Kc at 298. Here I need help. Yeah, I know there's an exponent. I just can't remember. I think it's delta H over R.
Negative delta H reaction times 1 over T minus.
Yeah, I knew the temperature part. I just wanted to make sure. Negative delta H of reaction over R times the difference between the inverse temperatures. So that's, you combine these two to make one equation. And then the second equation is the energy balance equation that we put up on the board, T2, and then it was x2 minus x1. And you just solve them simultaneously just like you did in the first one. Solver or MATLAB or whatever. Any other questions? Okay, now we're going to make sure there's nothing else in here that I care about. Okay. And what would this look like for an endothermic reaction? Right? I'm going to start at some temperature. And what's going to happen inside the reactor if it's endothermic?
Temperature's going to decrease.
Temperature's going to drop. We go to 95%. And then what do? We heat. And then same thing. Heat. Heat. Okay? Yeah.
So is this only true for an irreversible reaction where the conversion doesn't change across the heat exchanger, or is that just bothering me?
I understand what you're saying. So first let's start with, does this reaction, is this a reversible or an irreversible reaction? Reversible. Has to be, because these equilibrium constants, equilibrium conversions are not 1 or 0. Those are irreversible reactions, right? Where the equilibrium conversion is essentially 1. So this is a reversible reaction. Why is it that we can safely assume that nothing happens within the heat exchanger? I know what you're thinking. You're thinking, why would it not change if I'm heating it up inside a heat exchanger? What type of reactor could this be? Yeah. So if these were PVRs instead of PFRs, does that make you sleep better at night? But you're right, that if all it was just a PFR, no catalyst of any kind, and then I put it into a heat exchanger and I heat it up, obviously the reaction is going to continue to occur within that heat exchanger. There's nothing I can do to stop it unless I had some magical heat exchanger that separated my reagents, which doesn't exist.
And wouldn't you just undo everything you just did by cooling it back down?
No, because the heat exchanger volume is not the same as your reactor volume. So how much reaction occurs within that heat exchanger is a valid question, but if the volume is small compared to the volume of my reactor, not a big deal. Right? In other words, if the fluids are only in there for a second, then yeah, you're going to be putting them up to a higher temperature and then reacting them some more. So some of the reaction might start in the heat exchanger, but you want it to, right? I mean, it doesn't matter where it starts. It doesn't really matter to you. But how much reaction occurs in the heat exchanger? Yes, technically this isn't going to be a perfectly straight line if this wasn't a catalyzed reaction. Some reaction would continue in your pipes and all that kind of stuff. Any other questions? Okay, so the last thing that we'll talk about, and this segues nicely into what we're going to do next, is we're going to set up but not solve equations for a PBR. Unless you guys want to, I can pull it up on Excel depending on how much time we have left. But otherwise, we'll wait and we'll actually solve them together once you guys have a chance to bring your own computers. Okay, so if we have an exothermic reaction, what is the best temperature I can use to carry out this reaction? You said 5 Celsius?
It's like real low.
Yeah,
5,
low.
real low.